So we were discussing about stability and Routh Hurwitz criterion. Let's continue that. So before we move the details, a brief review of what we did in the last class. So we had seen in terms of transient response or the natural response, the system is said to be stable. A system is said to be stable if the natural response approaches zero as time tends to infinity. If the natural response diverges or grows without bound as time tending to infinity, then the system is said to be unstable. Any system in which the natural response neither grows nor decays, but it remains a constant or it oscillates as time tends to infinity, then such a system is called a neutrally stable system or marginally stable system or limitedly stable system. That was pertaining, this definition of stability was pertaining only with respect to the transient part or the natural response. Now, if you consider the response in totality, in whole, both the transient and the steady state together, then we have the notion of what is called BIBO stability or bounded input, bound output stability. A system is said to be BIBO stable if every boundary input yields a bound output. Okay. Then we took some examples. When the transfer function was k by s plus a, we had seen that the impulse response was exponentially decaying and the system is stable. So when the pole is in the left half, the system is stable. And the pole is in the right half, the system is unstable. Okay. So again, when you have unrepeated pair of pole on the imaginary axis, the system is marginally stable or limitedly stable or neutrally stable. And if there are repeated pair of poles on the imaginary axis, then the system is unstable. Okay. So it means that j omega axis in the S-plane is the stability limit or stability boundary. So long as the poles are in the left half, the system is stable. If the poles are in the right half, the system is unstable. If there are unrepeated routes on the imaginary axis, then the system is limitedly stable or marginally stable or neutrally stable. But if there are repeated routes on the imaginary axis, then the system will be unstable. So Routh Hurwitz criterion will help us to investigate whether a given closed system is stable or not without factorizing the characteristic polynomial. What is the Routh stability criterion? A necessary and sufficient condition for stability is that there should be no sign changes in the first column of the Routh array. Otherwise, the system is unstable and the number of sign changes in the first column of the Routh array corresponds to the number of closed two poles in the right half of the S-plane. Okay, so the number of sign changes in the first column will tell you how many poles are in the right half of the S-plane. Okay, and we have taken up one example as well, right? So this example we discussed, and we found that the closed loop system is unstable. Moving on, another numerical example. Determine the stability of the closed loop transfer function given below. This is the closed loop transfer function. Okay, so what's the characteristic equation? 1 plus GSHS equal to 0. What is that? That will be s raised to 5 plus 2s raised to 4 plus 3s cube plus 6s square plus 5s plus 3 equal to 0. So again, as before, we have to start with the root table. Starts from highest power of s up to s raised to 0. S cube, s square, s raised to 1, s raised to 0. What will be the first row? All the alternate elements. 1, 3, 5. 1, 3, 5. All the missing elements will constitute the second row. 2, 6, 3. What will be the next element? 2 into 3, 6 minus 1 into 6. So 6 minus 6, 0. Next thing, 2 into 5, 10 minus 1 into 3. So 10 minus 3, 7, 7 by 2. So here we cannot proceed further. Why? Because the pivot element has become 0. Okay. So that means we have to overcome this thing. Okay. How to do that? For that, we will consider a very small positive number epsilon. If only the first element in a row of an array is 0. Keep in mind, here we had a row whose only first element was 0. Other elements were non-zero. Okay. So when you encounter such a situation with a row whose first entry only is 0, then we have to consider a small number epsilon. Okay. Epsilon may be positive or negative. Okay. And then you complete the array. Okay, so instead of 0, you consider a very small number epsilon, which may be positive or which may be negative. Say, for example, 0.001, or epsilon may be minus 0.001. Okay, then the signs of the entries in the first column can be determined as in the usual manner. Okay, so going back, So instead of this 0, I will consider a small number epsilon, right? Say my epsilon is 0.001. So now you consider complete the array by considering epsilon. What will be the next entry? 6 into epsilon minus 7 divided by epsilon. 6 into epsilon minus 7 divided by epsilon. What will be the next thing? Epsilon into 3 minus 0 divided by epsilon. That means 3. What will be the next thing? This into this minus this into this all divided by this. So you will get the table like in this manner. Okay. So you have completed all the table. All the entries of the array have been entered. Right. Now what next? Just look for the first column. Right. 1 is positive, 2 is positive. So suppose epsilon is very small positive number. Say for example 0.001. Right. Then epsilon is also positive. So what happens to this? This becomes what? 6 minus 7 by epsilon. Correct? 6 minus 7 by epsilon. Epsilon is very small number, which means what? This number effectively will be less than 0. That means it is negative. Again, coming down to here, 6 epsilon square. Epsilon is 0.001, so epsilon square will be even smaller. Okay, so this part can be ignored. So what will you get? 42 into 0.001 minus 49. Okay, divide by 12 into 0.001 minus 40. So this will be effectively greater than 0. Fine. So what happens? There are two sign changes, plus epsilon to minus this thing and minus to plus. So there are two sign changes. So that means two poles are in the right half of the S-plane, which means system is unstable. Okay. Now let us consider you are considering epsilon to be negative, say minus 0.001. Okay. So what happens? So if let me remove this. Okay. So now suppose your epsilon is negative, you are considering minus 0.001. So you see that's a sign change, plus to minus. Okay. Now what next? Epsilon is negative, right? So what will be this? This will be 6 minus 7 by epsilon. Epsilon is negative, that means this part will be effectively positive, right? So from minus to plus, there is one sign change. And here what happens? It will be again, so plus to minus, minus to plus. Okay, and this will be again positive, right? So the row at which the sign change occurs will just change, but effectively the number of sign changes will be the same. It will be 2. Okay, that is why it is written. You can consider either epsilon from positive side or negative side. The number of sign changes will be the same. Okay, but the row at which sign change happens may be different, because you see, if epsilon was positive in the previous case, there was no sign change here. But now since there's a epsilon is negative, plus 2 to minus epsilon, that's a sign change. Okay, that's the only difference, right? So there will be two sign changes and hence the system is unstable. Okay, now let us take another example. Determine the number of right half plane poles in the closed loop transfer function. So this is the given transfer function. So we will start as usual from s raised to 5, s raised to 4, s cube, s square, s raised to 1, s raised to 0. What will be the first row? 1, 6, 8. Second row will be 7, 42, 56. What is the next thing? 42 minus 42 by 7, 0. Next thing, 56 minus 56 divided by 0. So now you have come across a row with all the entries 0. Okay. Previous one was the case where we had a row only with first entry is 0. But here we have a case wherein all the entries of a row are 0. Right? So it means that then this condition, a row full of zeros, means that there are symmetrically located roots about the origin of the S-plane. What do you mean by that? For example, this is your S-plane, sigma j omega. So this condition, a row full of zeros, means there will be symmetrically located roots about the origin of the S-plane. That means this may be the case. This may be one probability. Okay. It is symmetrical about the origin, or maybe like this. Again, symmetrical about the origin, or can be like this. 4 rows. Symmetrical about the origin still, or it may be a combination of all these. Okay. That is the meaning if you come across a case where a one row is, all the elements in a row are 0. An entire row of zeros will appear when the characteristic equation has roots symmetrically located about the origin of the S-plane, right? That's what is shown here. Can be like this, AA or BB or CCCC, or it may be a combination of all these things. So if you come across this situation, then we have a row, an entire row of zeros. So how to overcome that? You have to create an auxiliary polynomial. Okay, auxiliary polynomial is always of even order, right? How will you create auxiliary polynomial? Out of the coefficients immediately preceding the zero row in the Routh array. Okay, so you will get a row of zeros, right? So you take the row immediately above that. Consider the row immediately above that zero row. So auxiliary polynomial is made out of coefficients from that particular row. The row of zeros in the Routh array is then replaced by the coefficients of the first derivative of the auxiliary polynomial with respect to S. Then the signs of the first column are examined in the usual way. So coming to our problem. So what is auxiliary? So S cube is the zeroth row. All entries are zero in S cube row. So you consider the row immediately above that. That means S raised to fourth row. So what will be your auxiliary polynomial? Your auxiliary polynomial will be 7 S raised to 4 plus 42 S square plus 56. Okay. So it is an even polynomial. What do you mean by even polynomial? One in which the power of S is always even. This S raised to 4, this S square, this S raised to 0. Okay. So your auxiliary polynomial in this case will be 7S raised to 4 plus 42S square plus 56. What you have to do, you have to differentiate that. So dA by ds. What will you get? 28S cube plus 84S. Okay. So instead of this 0, 0, you substitute that coefficient 28 and 84. Okay. Now you can continue the table. Okay. So if you continue the table, you will see that there will be no sign changes. Right? So how will you continue that? Next thing will be what? 28 into 42 minus 7 into 84 divided by 28. Then, like that, you can continue all the other entries of the table. So you will see that there will be no sign changes in the first column. Okay. So does it ensure that the system is stable or not? Okay. There are no sign changes in the first column of the Routh table, right? Does it mean that the system is stable or not? A row full of zeros means any of these conditions. Okay, let us take one example. Suppose, so here you see which row was 0? It was S cube row was 0. That means there should be 4 rows symmetrically located. So it can be a case like this. Okay. Is this the case? Can you just tell me, can this be a case? No. Why? This is ruled out. Why this is ruled out? Because there is a one pole in the right half. So naturally there should have been a sign change. But if you complete the table, you will see that there are no sign changes. So that means this option is ruled out. Okay. Then what is the next probability? Next probability is that maybe a case like this, AA and BB. Or it may be like this, sigma j omega. It may be AA repeated roots. Okay. So to determine that, you have to factorize the auxiliary polynomial. Okay. So you see, what is your auxiliary polynomial? Your auxiliary polynomial is 7s raised to 4 plus 42s square plus 56. Okay. If this is the case, if you have a repeated pair of poles on the imaginary axis, then there will be no sign change, but you have to factorize the auxiliary polynomial and see whether this is the case actually or not. Okay. If this is the case, the system is unstable, because as per our definition, if there are repeated roots on the imaginary axis, the system is unstable. Okay. But this will not be reflected like sign change here in the right in the Routh table. Okay. So you have to factorize your auxiliary polynomial to check whether this is the case or whether this is the case. Okay. So let us factorize that and see what we are getting. How will you solve this? You put s square equal to x. So what will be your auxiliary equation? 7x square plus 42x plus 56 equal to 0. Okay. So x value you will get, from which you can find the values for s. Okay. So you will see that this particular example, this is the case. There are 4 rows like this. JA minus JA and JB minus JB. This is the case. So what can you conclude about the stability? System is not stable, system is not unstable, but the system is marginally stable or limitedly stable. Okay. There are no right half plane poles. Let us try next question. Determine the range of K for which the closed loop system shown below is stable. Okay. So this is the closed loop system. What's the first step? You have to create the Gaps equation. 1 plus GSHS equal to 0. So what will you get? You will get K plus S into S square plus S plus 1 into S plus 4 equal to 0. Right? So what will be your Gaps equation? Your Gaps equation will be something like this. S raised to 4, your Gaps equation will be what? S raised to 4 plus 5s cubed plus 5s square plus 4s plus k equal to 0. So you have to create a root table, right? So you will get 1 5k and 5 4. How will you calculate this element? This is nothing but 5 into 5 minus 1 into 4 whole divided by 5, 21 by 5. What will be the next element? 5 into k minus 1 into 0, 5k divided by 5k. So you can continue the table in this way. Okay. Now what's the question? Question is to find the range of k for which the closed loop system shown below is stable. So when can system be stable? If there are no sign changes. 1 is greater than 0, 5 is greater than 0, 21 by 5 is greater than 0. So there should be no more sign change in the first column. That means this should be greater than 0 and k should be greater than 0. So from here we will get one condition, k should be greater than 0. And from here you can find the limiting value. Okay. So 84 by 5 minus 5k equal to 0. From which your k will be equal to what? K will be equal to 84 by 25. Right? So for stability, k should be in the range like this, 84 by 25. It should be between 84 by 25 and 0. Now one question. What happens if k is equal to 84 by 25? If k is equal to 84 by 25, then S1th row becomes 0. Means what? There will be two poles symmetrically located about the origin of the S-plane. Okay. So if k is equal to 84 by 25, then you will have two roots symmetrically located about the origin of this plane on the imaginary axis. Means what? There will be sustained oscillations. Okay. So what will be the frequency of the sustained oscillation? Root of 4 by 5 radians per second. Okay. Because what happens? Two poles are on the imaginary axis at j root 4 by 5 and minus j root 4 by 5. Okay. So k should be between 0 and 84 by 25 for stability. If k is equal to 84 by 25, it is marginally stable, and if k is greater than 84 by 25, the closed loop system becomes unstable. Understood? Next problem. Determine the allowable region of stability for the closed loop system shown below. Okay. So you have to, what is the procedure? So you have to create the Gaps equation. What is Gaps equation? 1 plus GSHS equal to 0. Right? What is h of s here? H of s is 1. Okay. So here we have determined two parameters, kp and k. So this will be your root table, and from here there should be no sign change for system to be stable. So k should be greater than 0, and from this condition you will get your kp must be greater than 1 by 3 times ki minus 2. So if this condition is met, then the system will be stable. So we will end up this section with a practical example of stability. Okay. So this example video I have got from YouTube. Right. It is pertaining to a bridge called Takoma Narrow bridge in US. Okay. Let us see that. So with that we will wind up for the day. Thank you. you can see how the bridge is swinging. Okay. So see the amplitude of the oscillations. What is happening? It is growing with respect to time t. And eventually the bridge will collapse. Yeah. So we'll stop here and meet again for a new lesson. Thank you.